I'm Dr. Lakshmi Ravishankar, and in this module we'll be discussing about the Cope rearrangement. So at the end of this module, the student should be able to identify a Cope rearrangement, analyze a Cope rearrangement based on the frontier molecular orbital theory, determine the stereochemical outcome of a Cope rearrangement, write the products of an Oxy Cope rearrangement, and determine the stereochemical outcome of an Oxy Cope and an anionic Oxy Cope rearrangement. Before we go into the 3,3 sigmatropic shifts, how the Cope rearrangement, let us quickly recapitulate the sigmatropic rearrangements by way of some examples. So you see here that there are two reactions, two steps involved. The first is the migration of a hydrogen from this carbon to this carbon, so which is basically a 1, 2, 3, 4, 5, involves a 1,5 hydrogen shift. You could also have deuterium migrating as is seen in the subsequent step. So here deuterium is migrating from here and coming to this terminal carbon. Again, it's a 1,5 sigmatropic deuterium shift. It involves 6 electrons. A similar system of 6 electron migration involving carbon can be seen here. So this bond is being broken and it is now migrating here. Again, the counting has to be along the Pauline chain. So you see that this is a 1,5 superficial carbon shift. A subsequent 1,5 superficial hydrogen shift results in the formation of the product. A 1,7 shift of hydrogen is also possible. This involves 8 electrons, which is a 4n system, and like we saw in the previous module, superficially it will take place under photochemical conditions resulting in this product. A 1,7 hydrogen shift is a very important stage or a crucial step in the synthesis of vitamin D from cholesterol. This is the precursor to vitamin D, and you see here that this hydrogen has migrated from this methyl. So 1, 2, 3, 4, 5, 6, 7 undergoes a 1,7 sigmatropic shift to give you vitamin D2. So coming back to the Cope rearrangement and Claisen rearrangement, these are classes of 3,3 sigmatropic shift. So these reactions involve a 3,3 sigmatropic rearrangement, and a Cope rearrangement involves carbon in its framework. Whereas a Claisen rearrangement takes place when you have allyl vinyl ethers or allyl phenyl ethers, and more about this we'll be discussing in the next module. So the 3,3 sigmatropic rearrangements, be it Cope or Claisen, they are the most widely used sigmatropic rearrangements, and the Cope rearrangement, what happens is a 1,5 diene isomerizes to another 1,5 diene. Looking at it this way, it looks apparently there is no difference between the reactant and the product, because the Cope rearrangement is a sigmatropic rearrangement with only carbon atoms in the ring. In its simplest version, it is actually as though there is no reaction at all. These are known as degenerate Cope rearrangements, where the starting material is identical with the product and the equilibrium constant for the rearrangement is 1. However, if you have substituents, they are capable of shifting the equilibrium to one side or the other. For example, the equilibrium between 3,4-dimethyl 1,5-hexadiene and 2,6-octadiene lies on the side of the more substituted pi bond. So this is more substituted, so the reaction is favored in the forward direction. The transition state for the 3,3 sigmatropic rearrangements involves 6 electrons, so it's a 4n plus 2 pi system, which is similar to the Diels-Alder reaction which we saw in the module on cycloaddition, and hence proceeds through a cyclic 6-membered transition state. And because you have a 4n plus 2 pi system, these transition states have aromatic character, which reduces the activation energy for the process. The Cope rearrangement of acyclic hexa 1,5 dienes typically takes place around 250 to 300 degrees, and the energy of activation is approximately 35 kilocalories per mole. So can we talk of some factors which can facilitate the reaction happening at lower temperature, and how can one reduce the energy barrier? So there are certain factors which affect the Cope rearrangement and favors the forward reaction. One of them is presence of substituents which can be brought into conjugation during the rearrangement, and if that happens, then the reaction is favored in one direction as a result of lowering of the activation energy of the process. For example, here you have 3,4-diphenyl 1,5-hexadiene system. When it undergoes the Cope rearrangement, you see that you are getting a conjugated system. This double bond is conjugated with the phenyl. Same is the case here. So this is more stable, so the reaction proceeds faster in the forward direction. Similarly, if you have rearrangement resulting in release of ring strain, then the rearrangement can happen at a low temperature. See, for example, this goes at even minus 40 degrees. If you have a hydroxy group which is then converted to an alkoxide in the third position of the 1,5-hexadiene system, this also results in a faster 3,3 sigmatropic shift. Degenerate Cope rearrangement we saw earlier. So this is an example of a degenerate Cope rearrangement where there is no difference between the starting compound and the product. Bulvaline is an interesting molecule. If you see, it has got 1, 2, 3, 4, 5. This is a 1,5-hexadiene system. Similarly here 1, 2, 3, 4, 5. This is also a 1,5-hexadiene system. 1, 2, 3, 4, 5. This is also a 1,5-hexadiene system. 10 carbons, it has a C3 symmetry, and it has got 1.2 million degenerate structures. Here I have shown only the migration of the AB bond, the AC bond and the BC bond. Similarly, you can have several such migrations and you see that there is almost unbelievably 1.2 million degenerate structures are possible for this fascinating molecule. So let us look at the frontier molecular orbital analysis. For this, there are two ways to look at it. One is we consider this. Imagine that you are breaking this here. This is an allylic radical. This is an allylic radical. So bringing two allylic radicals together to access for a possible interaction between the termini. Now you know that allylic systems have got 3 molecular orbitals, and a radical will have the side 2 is going to be the molecular orbital in which you will have the single electron. So that is known as the SOMO, or the singly occupied molecular orbital. So two SOMOs of two allyl radical systems combined together, it's a superficial overlap resulting in the formation of the product. You could also consider it, instead of considering it as two radicals, one could imagine that this is fragmenting here, this bond is broken. So one of them is a positively charged species, the other allylic is an anion. So the HOMO will be the allyl anion, which will be side 2, and the LUMO will be the allyl cation, which is also side 2. So you see there is a positive overlap, the like faces are coming together on the same side in the interaction between the two allylic fragments, and hence this reaction is superficially, it is an allowed framework. So the 3,3 sigmatropic rearrangement is a 6-electron reaction, and whichever way you look at it, the transition state involves the frontier molecular orbital interaction between psi 2 of one component and psi 2 of the other component, as can be seen here. And the way it is demonstrated or drawn here, you can see that it resembles a chair conformation, and we will see in the next slide that the transition state can be seen either as a boat or a chair, and it is the chair transition state model which is the favored model. So a thermally allowed reaction is possible in either of two geometries, the chair or the boat geometry, and this is the transition state for the chair-like transition state, and this is for the boat-like transition state. And extensive studies have been done on 3,4-dimethyl 1,5-hexadiene systems by taking diastereomers of them and seeing what is the stereochemical outcome of the Cope rearrangement. So if you take this, this is known as the cis isomer. If you try to draw this, it goes through a cyclic transition state. So the best way to do it is, imagine that you are having a chair, draw the chair conformation of a simple cyclohexane molecule, and one of the carbon-carbon bonds is not there. So this becomes my hexadiene system. You put the olefinic, the terminal carbons, there is a pi bond here, and now you see that you have two methyl substituents, both are above the plane. So that is a 1-2 relationship here between these two. This is 1 and this is 2. So 1-2 in a cyclohexane chair conformation, one has to be axial, the other has to be equatorial. And now imagine that I am forming a bond between this carbon and this carbon, this pi bond shifts and this double bond is coming here. There is a formation of a double bond here. Now you see that this methyl, this double bond is going to have the Z stereochemistry, and this double bond will be having the E stereo descriptor, or in other words, this will give rise to an EZ isomer. But if I were to take this kind of a trans type of a relationship, and do the same exercise. Now when it is 1,2 trans, you could have either the 2 methyls diaxial or it could be diequatorial, and you know that the diaxial is less stable because of the 1,3 diaxial interactions, the steric factors, and hence the transition state will prefer to exist in the more stable equatorial disposed methyl groups. So when this forms the double bond here, single bond here, this shifts here and this forms the pi bond, you see that the methyls are going to be like this. So in this case, this is going to be having the E stereo descriptor, this will also be having the E stereo descriptors, or in other words, this will be EE, which is going to be favored. If it were going through this, it should have been the ZZ, which is not observed. The same thing is illustrated here. If it is the trans, the more stable conformer is where it is diequatorial, you get the EE isomer. If it is the trans where the two substituents are diaxial, it is less stable, the ZZ isomer, but which is not observed. If you had the cis, then you would end up with EZ or ZE. The same thing is confirmed here. You have, if you see this, this is going up, this is coming down. So this is my trans which we saw in the previous slide. So confirmation that it goes through the chair conformation and not through the boat, because if it were to go through the boat, it should have given me a trans cis type of geometry in the product, which is not observed. Similarly here, if you take the cis isomer, if it were to go through the boat, it should have given me a trans-trans geometry, which is not observed. So all these results suggest that the transition state for the Cope rearrangement proceeds through a chair-like transition state. Coming to the oxy-Cope rearrangement, if I have a hydroxy group in the third position of the 1,3,1,5-hexadiene system, then we are talking of what is known as an oxy-Cope rearrangement, and these proceed efficiently at low temperatures, especially when the alcohol OH is converted to the alkoxide. And this is known as the anionic oxy-Cope rearrangement, and the enhanced reactivity is because the negative charge is more delocalized in the transition state than in the starting material. So this is my 3-hydroxy 1,5-hexadiene system. Now in the absence of a base, it goes in this direction to give me this ketone, aldehyde, this aldehyde, but it's a slow process. However, when you add potassium hydride, this forms the O-, the alkoxide, and the reaction is faster and it undergoes the 3,3 sigma tropic shift to give me the aldehyde at the product. Like we saw in the Cope rearrangement, here also it prefers the chair-shaped transition state, and the ratio of the stereoisomers of the products depends on the orientation of the substituents in the transition state. A substituent at C3 or C4 of the 1,5-diene generally prefers the less hindered equatorial position. So this is my substituent on the C4. If I count this 1, 2, 3, 4, it is the C4. If I count it from here, it becomes C3. Now this substituent prefers the less hindered equatorial position, and you get the E-alkene isomer of the product. So to summarize, the Cope rearrangement is a rearrangement of 1,5-dienes to isomerize to another 1,5-diene involving 6 electrons. So it's a 4n plus 2 pi system, proceeds through a cyclic aromatic transition state. If I have substituents which can stabilize the product by conjugation, or rearrangements which result in release of ring strain in the starting 1,5-dienes, will favor the product formation. This is resulting in release of ring strain. Please remember that. Presence of an alcohol or alkoxide substituent on the C3 carbon of the diene favors the 3,3 sigma tropic rearrangement. This is the oxy-Cope rearrangement or the anionic oxy-Cope rearrangement. Both Cope and oxy-Cope rearrangement proceed through a chair-shaped transition state. So with this, we will come to the end of the Cope rearrangement. In the next module, we will be discussing the Claisen rearrangement. Thank you.